Okay, so moving on from the optimizations that we have discussed, the next thing that we are going to look at in a little bit is verification and validation, right? So we have already been through this to some extent, so I'm just going to sort of reiterate some concepts over here. Verification essentially is about ensuring functional correctness. And why is it a challenging problem? Because designs are increasingly becoming more complex, which naturally is going to make verification more difficult. The biggest problem over there is that errors that are found late in the design cycle are much harder to fix, or more importantly much more expensive to fix, because they usually require going back and repeating a lot of the work that has already been done, or making changes maybe after hardware has come out, which actually are much more impactful, right, or impactful in a negative sense over here, right. They actually are much harder to fix than what was earlier there. The scope of verification, usually we have talked so far only about functional correctness, but it can also include so-called performance requirements. Is my design going to be fast enough to meet my required throughput, let's say, right? Which ultimately means that you need to have comprehensive approaches that are needed for different aspects of the design. And it also comes up, at the end of the day, what is the goal of your verification? It is to build confidence that the design is correct. Because as you might have noticed from the test benches and so on that we wrote, what we end up doing with test benches primarily is testing a few cases. The biggest problem that can arise in such a scenario is, what if I missed out some test cases, right? And in that case, if your test benches are not good enough, you essentially have this problem that you don't have confidence that your design is actually as good as you would like it to be. Now, so far we have talked about verification, but there is also this additional word called validation. And validation usually comes up after you have entirely verified the design and you are then going forward to the next stage, which basically says, okay, now I have got a product, is it the right product, right? So one sort of nice way of putting it is to say that verification is trying to ensure that we are building the product right. What does that mean? It basically says that you have a certain specification, are you meeting those specifications? Whereas validation is ensuring that you are building the right product. It's sort of a play on words over here, but if you think about it, this is basically ultimately what it comes down to. Is the problem being solved the right one in the first place, right? Verification does not necessarily look at that. Verification says that you already have a specification on what needs to be built, and you are only saying, okay, I have written Verilog code for this, does it pass these tests? And those tests are what determines whether your verification is correct. Validation is taking one step back and saying, are those the right tests? Are those even the right things to be looking for? Is the product being built the right one? Okay. So typically the way that it works is, you have a design, you go through a verification process and you keep iterating on this, right, fixing problems or bugs in the design and re-verifying it until you have got the entire thing working as you would like it to be. Once verification has passed, or you have gone through a certain level of verification confidence, you can go through to implementation, which is typically the compilation process and getting hardware and then doing optimizations, and then you go through to the validation problem, right? Now this implementation would include things like my RTL coding, debugging, which of course also includes some amount of verification. But then finally I've actually got a product, right, that I've built, and I now need to check whether that was correct, and if not, modify my implementation in order to get the final problems resolved. Only after everything has been validated does it even make sense to talk about the final deployment. Okay. So all the examples that we looked at so far in this course at least were primarily around this idea of simulation based verification, right? We had test benches where we would instantiate a design under test, we would apply certain stimulus and check the responses, right? Now within this we also had certain things where we would typically do something called directed testing. For example, if I know that I am adding two numbers together, I would have some amount of manually crafted test cases where, for example, I know that if I add 0 to a number, the other number is what should come through as the result. If I am multiplying, I know that multiplication by 0 should give a 0. So those are test cases that I know have to be tried out. But let's say I am multiplying two 16-bit numbers, the number of possible combinations of two 16-bit numbers is 2 power 32 different combinations, right, 2 power 16 into 2 power 16. If I am trying to verify, let's say, a 32-bit multiplier, it becomes 2 power 32 into 2 power 32, which is essentially impossible to do in any realistic amount of time. So then what I instead do is go for randomized testing, right, where I say, okay, look, I'll do some amount of manually crafted test cases and then throw a lot of random tests at it. If it passes both of those, I have a high degree of confidence that my multiplier is working correctly, right. Now, there can be other scenarios where you have certain constraints on what your inputs are allowed to be in the first place, right, in which case maybe you could actually reduce the number of test cases that you need to consider by applying those constraints and saying, look, I don't need to test all possible scenarios, I only need to test for a few of them. That's called constrained random testing, and there are techniques by which you can actually generate automated test cases after applying certain constraints on what the inputs are going to be like. We also discussed this idea of running test suites automatically, right, and the idea was that you come up with a set of unit tests or small test cases that your system always needs to pass, and the idea is as and when you add any new features or you make any modifications, you go back and run a regression test. Did any of the previously passing tests start failing now, right? That's called a regression and is something that you generally always want to avoid. And finally, simulation, right, especially Verilog simulation, tends to be slow. So it may be that you can't actually afford to simulate everything directly in Verilog. You might have to abstract certain things out and perform your simulations at a higher level of abstraction. Now, within the concept of verification, right, or simulation based verification, there are also a certain kinds of constructs that we came across, right. Assertions were something that we were using consistently, right. For example, I could add in something like, I have a so-called immediate assertion where I basically apply a condition and I basically check whether a particular value is satisfied over here. But I could also have something else which is called a concurrent assertion, which is almost like having a separate piece of hardware sitting in your design whose job is to monitor this value of what a particular signal is supposed to be, right. And in this case, it's not an assignment over here. This is actually checking at any given point in time that this value should be satisfied, right. It should be less than f, right. I could also have again some other kind of assertion which basically says, right, I have declared this property and I want to check that this property is always satisfied. So what does the property by itself say? It basically checks that count is less than this at every clock edge. And then I have an assertion that says at any point in time, right, this property should be satisfied, else it is going to give me an error condition, right. Now the point is that these are constructs of system Verilog. Other languages like VHDL have their own constructs that allow various kinds of property testing and so on, right. But the idea of an assertion is not necessarily restricted to a language like system Verilog, right. It's a more abstract concept. It sort of tells you that there are certain properties or invariants that you need your code to be satisfying at all points in time, and if you can encode those in a certain way, right, and make it part of your code, then it makes it easier to verify your designs properly. There is also this notion of so-called coverage driven verification, right, which is an interesting concept. Effectively what we say is, especially when you are dealing with code or designs that go into multiple tens of thousands of lines of code or possibly even hundreds of thousands, or there can be scenarios where you are dealing with millions of lines of code, it's manually impossible to know everything about about your design and whether it's working properly. Instead, what you would like to say is, I have test cases, how much of the code is actually covered by those test cases, right. So as we already mentioned, right, I mean, even for something as simple as a multiplier, I cannot test all possible input combinations. Now let's say you have something like a CPU which includes a multiplier as one of the design units, right. Now clearly the number of different states or different combinations of inputs that are possible is so large that you can't even think of testing all possible scenarios. So instead a sort of proxy approach is taken which says that, can I at least say that each line of code that I have written has some test that covers it, right? Each function or each design feature that I have implemented has some kind of a test that covers it, right? And for specific kinds of signals, am I checking them under, especially for control signals, am I checking what happens as they toggle? What happens when it's 0, what happens when it's 1? Obviously you need to restrict this, you can't do this for every input of a multiplier for example, but it makes sense to do it for example for the control signals going into a multiplexer, right? This is sort of related to the idea of branches and saying, okay, am I sort of covering all the possible branches that exist, right? So coverage metrics are essentially a sort of proxy for the fact that we cannot cover all possible scenarios in a design, but at the same time they help to increase the confidence that you are able to actually look at the different possible scenarios. Now it turns out that System Verilog has this notion of so-called coverage groups. This is more or less out of scope as far as this course is concerned. I am just sort of mentioning it in passing as something that you might look into when you go into more advanced use of System Verilog, but we are not using it as far as this course is concerned. What it allows you to do, for example, is to define a so-called coverage group, and the idea behind a coverage group is actually very simple, right? It basically says that A has, let's say, a few options, right? I'll call it A1, A2, A3. B maybe has some other options, it has B1 and B2, and well, in this case the op, right, has some other options, let me call it op1, op2, op3, op4, right? And I can imagine now combinations like this, right? A1, B1, op1 is one input combination that I have to deal with. Similarly, A1, B1, op2 is another input combination. Hopefully, right? Obviously, it is already obvious how many such combinations are there. I basically have number of elements in A into number of elements in B into number of elements in the op set, right? This is the number of different combinations that exist. Now, we are not saying that we are going to cover every single one of those combinations, that becomes unrealistic. But what we would like to do is, can we at least have some kind of different test cases that we apply, and then say based on this I am at least covering all of the different possible values of A, the different values of B, the different values of op, but maybe not all possible combinations that we have here. At least make sure that A is touched upon, B is touched upon, op is touched upon, right? Or you might specify that yes, I also need to test all possible combinations of these. So then you might identify specific bins over here. So for example, you can see that I might define that, you know, I want to make sure that the all zeros and all ones cases are satisfied, but in the others I am not necessarily looking at all the possible combinations. I might be only interested in at least some of them are being tested, right? So that's one way by which we can create different combinations, and then there are actually things which allow us to create these coverages and create randomized samples from those coverage groups, right? Once again, as I said, the point over here is not necessarily that, you know, this is an aspect of System Verilog. This is, you need to think of this more in terms of what is the problem it's trying to solve. It's taking a step back and saying, how can I maximize the coverage in general? If the language you are using, let's say it's VHDL, if it does not have exactly the same constructs, it will have some other way by which you can achieve a similar kind of purpose. What is more important is how do you think about the problem in the first place, right? I need to identify which are the important combinations and then ensure that I cover as many of those combinations as I can. Now, a lot of what we do involves both hardware design as well as software, right? And typically that means that we need to co-verify, meaning that we have some parts of our code already being tested in software simulation. We also have some parts being done in hardware simulation, right? This becomes especially relevant when we are either trying to design a new CPU where we have some parts that are running in hardware already on the basic system, but then there are some things that are only being emulated in software, Or we might be looking at, let's say, a hardware accelerator design where we know that part of our system is going to run in software, but at the same time it will need to exchange data with actual hardware and run it. What that means is we actually have a system where I can do a software simulation talking to a hardware simulation, but after I have implemented both of those, I would now have a hardware software interface where the actual thing runs on real systems, right? So the software under test would run on a CPU, the hardware under test would run on whatever hardware we have implemented, maybe an FPGA, maybe an ASIC, and there would be some kind of an interface that allows them to communicate between each other, communicate with each other. So co-verification in turn leads to a number of different problems of its own, right? You might find that you need to do co-simulation where the software is fine, it actually can run on the CPU that it's finally going to run on, but the hardware, you don't really have the hardware ready yet. What you do is you allow the hardware to run in a simulation environment like Verilog, and you figure out some way by which the software can communicate with a Verilog simulator, so that you are effectively transferring data in software which does not have a notion of a clock to a Verilog simulator which has the notion of clocks and concurrency and so on, and get the data back from there, right? Now this can become very slow, right? What happens in that scenario is that the Verilog simulation is typically going to run much slower than your actual software that's running on the system. So instead, very often what we do is, if we know that the software we are building is actually, let's say, a CPU, we don't go and simulate the entire CPU in Verilog. We instead create something called an instruction set simulator or some kind of a cycle accurate simulator of the system, which is fast but is not accurate down to the individual gate level. If that is not satisfactory, you might actually have to go for a full-blown RTL simulation, Verilog, right? It's more accurate, but it can be orders of magnitude slower than if you are able to come up with a abstraction like an instruction set simulator that runs faster. Now increasingly there are notions of hardware acceleration and FPGA prototyping where we actually try and use FPGAs as their nice powerful bridge between what's available in terms of hardware and the fact that it can be made programmable, and use those either to actually speed up your simulation or actually maybe directly to even prototype part of the hardware that you are trying to build, right? So let's say that you are trying to design a new CPU, you make sure that the code that you have written is completely synthesizable and will actually run on an FPGA before you then finally go through and optimize it for running on custom hardware. So all of these are different techniques that sort of allow you to bridge between the software and the hardware aspects of things. Now all of this was what falls more or less under the category of simulation based verification. There is also the notion of formal verification, which I am just sort of touching at a high level over here. The idea of formal verification is that you can actually mathematically prove that a particular design is correct, right? So rather than just throwing a lot of test cases at the problem, you should be able to take your code and literally say, as long as what gets implemented is a correct interpretation of this code, it is mathematically provable that it is doing the right thing, right? There are many different types of formal verification, including what falls under the idea of so-called model checking, where we are verifying properties against several possible states. So this can actually result in a so-called state explosion, right? The number of different states that you are trying to match up can become extremely large. There are ways by which you can sort of prove that two designs, possibly in different languages, have the same behavior. This requires a very careful, almost like compiler level thing, which is trying to translate both of those designs into a common language, right? And then sort of showing that they are equivalent. A lot of it revolves around the idea of proving theorems. As I said, these are mathematical proofs that we are looking at, and if we can sort of build up a systematic way to say that the compiler itself can show that these circuits are equivalent, then that's in some sense the highest degree of confidence that we can get that our circuit is going to behave properly. Now this is not just for circuits. formal verification and theorem proving apply even in the context of pure software implementations, right? They are typically used especially for complex control logic or scenarios like safety critical operations, things like nuclear power plants or spacecraft control software, right? There are a number of limitations, as I said, the state explosion problem and the complexity of how you even sort of specify the formal properties can be quite difficult, which is why there are a number of different limitations on when it can be applied. The important thing to understand is it's not an either or problem, right? It's not that you either do formal verification or you do simulation based verification. They are usually complementary to each other and both can be used to solve different aspects of the overall verification problem. An example of formal properties would look something like this, right? You define a property and you basically say at any clock edge, right, you cannot have two grant signals both being 1 at the same time, right? So this is just essentially specifying a property, right, and you can assert that property. Similarly, you can even have a more complicated thing which says that if there is a request after a certain amount of time, it is guaranteed that there would be a grant signal, right? So this is actually a more complicated thing to verify. It's difficult to even specify it as part of the language, although System Verilog provides you with some kind of ways by which these things can be specified. But in general, these are not normally parts of RTL design. Even using these things in a systematic way requires a careful understanding of how formal systems work. They can be extremely powerful when you are able to apply them in the right way. Now, finally, moving beyond even formal verification, we have the notion of so-called performance verification, right, where basically what we are saying is we want to go beyond functionality. It's not just is this correct, is it also good enough, does it meet our performance requirements? For example, does it give the correct data processing rate, the throughput, number of samples processed per second? Is the delay from input to output within the bounds that we can accept, right? What about the resource utilization that we have? What about the power consumption? As you can imagine, these are not easy to sort of verify directly using simulation, but there are other ways by which you might be able to do this. In certain cases, you might actually find that things like throughput and latency require you to actually simulate complete software systems, right, including the activity of a bus, including the activity of external signals that generate realistic workloads, and only then you can evaluate the performance. Things like critical path analysis are not really part of a simulation based verification. They are actually static analysis that can be performed in order to identify bottlenecks in the system. And finally, especially with bus based or NOC based systems, you might find that you actually need to do extensive performance simulations in order to evaluate the design under actual various conditions that might arise in real life. After all of this, right, remember that we have our original design which passes a certain test suite, but then we are going to optimize it to get a good hardware implementation. We need to make sure that the same tests pass there as well, right, and finally compare the results. So the problem here is we need to ensure that our optimizations don't introduce bugs of their own. This is entirely possible in practice, right? There are certain scenarios where, right, things like the equivalence checking is particularly powerful here, because if you can show that your compiler itself is built in such a way that your optimized code is functionally equivalent to the original, that is by construction you cannot have an error being introduced over here, that is probably one of the most powerful approaches that can be followed. Regression testing, corner cases and various verification strategies that you apply, all of these have an important role to play in how you can guarantee the correctness after you have applied various optimizations. Now finally, so far we have been talking only about verification, right? A word about validation. This is, as I said, verification is design centric. It ensures that the design matches the specifications, whereas validation is ensuring that the system actually solves the intended problem, right? Which means that you now need to start doing system level testing. You can't just test the individual adders and multipliers, you need to be able to put it against the original requirements and see if it solves the right problem. You need users to finally sign off saying that yes, this is actually solving the problem that we wanted. And the correct way of doing it, of course, is that you actually need to put it in the field and test it in its actual environment. So all of these different higher levels of testing become important when you are going for the actual validation, system level validation. There are a number of different ways that it can be done, of course. Early prototypes can be tested, some amount of benchmarking, specific use cases. As you might imagine, a lot of these things are related to how you also build up verification strategies, but validation is sort of an important problem in its own way, right? It's not just a sort of subset of verification. It has certain other qualities that set it apart from just the basic verification problem by itself.